Hi, I'm Tom Hausenbauer from Limnetics Corporation, where I have an ownership stake. We are a very small but aspiring manufacturer of floating machines using large propellers to circulate lakes and reservoirs. We're kind of a startup, except that we've got a 25-year head start developing our products and working out the kinks. About 15 years ago, we noticed that machines like ours are often used by small town water departments in Illinois for taste and odor issues, especially manganese. But we have not seen destratifiers widely used for other primary purposes, particularly internal loading of phosphorus and cyanobacteria control. So today I want to talk not so much about limnetics as about mechanical destratification in general, because we think that we may be only scratching the surface and that destratifiers can fill a bigger role in lake managers' toolboxes. One thing that might have been overlooked so far is ferrous iron. This slide's from Bob Kortman at GZE Geoenvironmental. Most of it's over my head. I'm just a mechanical engineer. The key point is the impact of ferrous iron as a limiting nutrient for cyanobacteria. There's a good article on this in last June's Lake and Reservoir Management. It's by Malat, who's done a lot of work on this. Mechanical destratification's been around for a while. It was originally invented and demonstrated by Professor Garton from Oklahoma State University in the 70s. They're sometimes still called Garton pumps. They use large propellers to push oxygenated water from the epilimnion down to the hypolimnion to increase dissolved oxygen at the sediment-water interface. More research was done in the 1980s by the Army Corps of Engineers under Richard Punnett. He developed performance criteria that were picked up by Rahman at the Illinois State Water Survey, who demonstrated the benefits in some Illinois drinking water reservoirs. For a long time, the first and only manufacturer that I know of was E.C. Baker. They're a well drilling company in Illinois who built dozens of these things for small towns. In the same general time period, Solar-Bee was using smaller devices to circulate water in the upward direction to get some of the same benefits. It's not the same as a Garton pump, but significant because of the number of units that they built, which I believe was in the hundreds. And also an Australian company called Weers has been manufacturing large Garton pumps since 1980s. They have some presence in North America, but we haven't seen a large number of their projects here yet. Since 2007, Limnetics has been working to establish ourselves and give lake managers an American option for destratifiers. We have a few projects in Illinois. These are some destratifiers that we know of in Illinois. Most were made by Baker, but I don't know of any new Baker units installed since 2012. Limnetics has done 4 installations, and I also know of 1 Weers unit in Illinois. Okay, let's look at some data from real lakes and reservoirs. These are typical dissolved oxygen and temperature profiles from 3 stratified lakes on the left and 3 lakes with operating destratifiers on the right. In all cases, the vertical scale represents depth in meters, with 0 representing the surface at the top, going all the way down to the bottom. The horizontal scales at the top are temperature in degrees centigrade, and at the bottom, dissolved oxygen in milligrams per liter. You can see a clear pattern in the 3 stratified lakes, where the temperatures remain in the upper 20s in the top part of the lake, drop through the thermocline, and tail off down into the teens at the bottom. Dissolved oxygens are in the 4 to 12 range in the upper part of the lake, the epilimnion, drop fairly sharply through the thermocline, and in the hypolimnion they drop to 0 and stay there all the way to the bottom of the lake. In contrast, the destratified lakes temperature profiles are pretty constant from top to bottom. They remain in the upper 20s in all 3. Dissolved oxygens are all in the same 4 to 12 range in the upper part of the lake, and where you've got a lot of photosynthesis going on. And then at the bottom, you've got more respiration and less light. They may tail off. but they remain above zero all the way to the bottom of the lake. What does it take to pick the right equipment? There are a couple things to look at. First, how much water do you need to move from top to bottom? We found two different recommendations for minimum flow, and both seem to agree with each other reasonably well in most cases. Weir's bases theirs on the full volume of the lake, and they recommend turning it every 25 days. Punnett, the Army Corps of Engineer guy, recommends using the hypolimnian volume only and turning it every 8 days. These would be only direct flows, not the indirect flow sometimes published. Direct flow is about 100 cubic meters a day for either a Baker 3 horsepower or a Limnetics 3 horsepower unit. It's about 12 cubic meters a minute for the largest solar bee. You also want to make sure that you're pushing water down deep enough to reach the bottom of the lake. This is an equation developed by Punnett to calculate the depth of the plume. And by the way, you can find links for all the details of this old research material on the Limnetics website. In the next few slides, I want to look at all three destratified reservoirs that I showed before and how they stack up against the two rules for flow volumes that I mentioned. I'll be using ratios to compare actual flow volumes with recommended flow volumes under both the Weir's and Punnett rules. A ratio of 1.0 would be perfectly sized, more than 1 is overpowered, and less than 1 is underpowered. Altamont Reservoir is 24 hectares and 9 meters deep. It has one Baker 3 horsepower unit installed in 2012. It's pumping 4 to 6 times the recommended minimum flow. We took data at 3 points moving away from the destratifier. The two graphs shown are the same data in two different forms. We like to see DO of 2 milligrams per liter close to the bottom. As you can see, we have 4 milligrams a liter at the furthest point, about 350 meters from the destratifier. Lake Paradise is the prime source for the city of Mattoon, Illinois. It's a 56 hectare and on the shallow side about 5 meters deep. It has 2 Baker units installed about 15 years ago. These units together pump 4 to 13 times the recommended flow. Dissolved oxygen and temperature are uniform throughout the basin. Otter Lake is larger than the other two, about 130 hectares. Depth is 9 meters. The last few years they've been running several solar bees to circulate the epilimnion without disturbing the hypolimnion. The unit you see here is a pilot unit installed this year by Limnetics. It's one of two pilots where we're trying an adjustable tilt angle, in this case 45 degrees, to generate horizontal flow and possibly give a larger area of influence. One 3 horsepower unit is underpowered for the entire lake, but we wanted to see if we could impact the lower basin where the water intake is located. The map shows the location of the solar bees as circles. The solar bees are still running, by the way. The destratifier is located at the south end, pointing north. We compared late summer DOs and temperatures at point A, which is in the middle of the main basin. Before destratification in 2020 is shown in red, and following destratification in 2021 is shown in blue. The Otter Lake Water Commission wisely brought the destratifier up to speed slowly in the spring. They didn't get up to full speed until the end of June. These readings were taken at the beginning of August. You can see that temperature is uniform compared to about 10 degrees difference between top and bottom last year. Last year the sediment was anoxic below about 4.5 meters. This year the DO is reaching the bottom, although not quite up to the target of 2 milligrams per liter that we'd like to see. A new destratifier will normally disturb the old sediment at first, so we expect it to take a while to get the DO up. Next year should be a better indication of how we're doing. What does it cost? These are typical for a 3 horsepower destratifier. Installation is usually going to come in under $40,000. Energy costs, about 10 bucks a day, are typical, although usually in the wintertime these things can be turned way down or off completely. For reference, here's some typical costs for other alternatives normalized to 100 hectares. To be fair, these aren't necessarily apples to apples comparisons. Hypolimnetic oxygenation can be used in much deeper waters and has some other advantages. Flow tubes can be added to mechanical destratifiers to go deeper, although I'm not ready to recommend that. I have concerns about maintenance. Small circulators are probably better suited for smaller water bodies, but if you need a lot of them, then it might not be the best application. Here are some advantages and disadvantages of mechanical destratification. It is a relatively inexpensive alternative. These are easy to get in and out of the lake, and they can be run in either the downflow or the upflow direction, or at least most of them can. On the downside, it does shake up the sediment temporarily at startup, which can have a negative impact on water quality. The warmer water does increase aerobic decomposition at the sediment and increase oxygen demand. It's not good for cold water fish. For example, trout don't do well above 18 degrees centigrade. And they also float in the middle of the lake, which can be a safety concern. Let's talk about safety. You do need to keep the public away from these things. We see a lot of variability in what lake managers decide is necessary for their public. Limnetics offers cage and fence options. Some operators say marker buoys are fine on their lakes. In any case, signs and beacon lights are a good idea. The National Electrical Code also has rules that apply. We see fountains all the time. The electrical hazards are pretty much the same. What's the best application for a mechanical destratifier? A 3 horsepower destratifier is probably overkill for anything under 10 acres, but 10 to 100 acres can likely be covered by a single unit. 5 to 10 meters is a good depth range. It probably stratifies, and it may be anoxic at the sediment, yet the bottom is within reach of a propeller without a flow tube. You have to have power available. Normal household single phase is fine. It's probably more economical than most alternatives if it fits these criteria. Where to locate a destratifier in a lake? Oxygenated water will move horizontally, but not down. So you do want to locate it in the deepest part of the lake, otherwise you'll end up with anoxic zones. And I have seen this. You may also need a second destratifier if you have ridges in the bottom of the lake. I mentioned earlier that mechanical destratifiers are relatively easy to get in and out. 3 horsepower units are usually delivered on a trailer. A crane may be necessary, but often can be launched from a boat ramp. Here are a few points that I hope you take away today. First, mechanical destratifiers are a tried and proven way to deliver oxygen to sediments up to 10 meters deep. They're economical for large water bodies, and they have the potential for other applications like internal phosphorus loading and cyanobacteria control. We have a lot to learn to reach that potential. We hope to see more research on how mechanical destratifiers specifically influence internal phosphorus loading and cyanobacteria. On our part, we need to pursue these last 3 points by collecting more data on the range of oxygen spread over the sediments, and also to verify our sizing methods. We also think machines larger than the standard 3 horsepower make sense, so we hope to go bigger in the future. We had planned to have a booth in Oklahoma City this week to talk about this stuff in person, but we certainly respect NALMS' decision to do it this way. In any case, the Limnetics website has plenty more material on these topics, or we would love to take your calls and discuss more. I understand we have a few minutes now for questions and discussion.